Okay, we're very happy to have Piotr Gruza here from Warsaw to talk about tightness and solidity in fragments of piano arithmetic. Go ahead.
Thank you very much for giving me this opportunity to speak today about this topic. This talk is based on the joint work with Leszek Kołodziejczyk and Mateusz Łewyk. Let's start with preliminaries. We say that a theory A interprets a theory B if and only if there exists a translation of all symbols of the signature of B, including equality, into the language of A, such that the translations of all axioms of B are provable in A. And we will use triangle to indicate that A interprets B.
Piotr, can I quickly ask a question? We do ask questions here, at least we should.
Yeah.
So does it mean that equality may be translated to something else?
Yes.
Okay.
Maybe, yeah, to some formula. Yeah.
Thank you.
Okay. And similar definition we make about models. So we say that a model M interprets a model N if and only if there exists a translation of all symbols of the signature of N, including equality, into the language of M, we allow for parameters, such that the structure constructed in M by using this translation is isomorphic to N. So in other words, we have in M, we have a formula, maybe with some parameters from M. We have a formula for domain. We have a formula for equality. We have formula for each symbol of the signature of N. And if we use this formula to build a model inside M, then we obtain something which is isomorphic to N. And again, we will use triangle to indicate that M interprets N. Interpretations can be composed, and each theory can interpret itself via the identity interpretation. And with this, we can make the following definition. We say that theories A and B are bi-interpretable if and only if there are interpretation of B in A and interpretation of A in B, such that compositions of these interpretations are provably isomorphic to identity interpretations. So in other words, there is a formula which is provably an isomorphism from identity interpretation to this composition. In the picture, it looks like this. A theory A interprets B, theory B interprets theory A, and we have this isomorphisms. And the similar definition we can make for models. Let's look at some examples. So, for example, PA is bi-interpretable with ZFC minus infinity axiom plus negation of infinity axiom plus every set has a transitive closure. And for negative example, ZF and ZFC plus GCH are mutually interpretable because in ZF we can, for example, construct constructible universe L. But as we will see later, they are not bi-interpretable. And we are now closer to the topic of this talk. So Albert Wieser proved the following theorem. If we take any two extensions of PA in the same language as PA, then if they are bi-interpretable, they are equal. So distinct extensions of PA are not bi-interpretable.
But do you mean complete extensions or just extensions?
Any extensions, I mean well, here when I say theory, I mean deductively closed theory.
I see. So they both add something to PA. They are not just PA.
Well,
So-
they may be PA. So if we take, for example, PA
and something
and
else.
PA
Right.
plus con PA, they are
Right.
not bi-interpretable.
I understand. Thank you. Thank you.
Yeah. And Ali and I had called this property tightness, and proposed to look closer at it. Maybe define it properly. So we say that a theory is tight if for any two extensions of it, A and B, in the same language as this theory, if A and B are bi-interpretable, then they are equal. Ali and I have proposed also stronger notion called neatness. So here we say that a theory is neat if and only if for any two extensions of it in the same language, again, A and B, if A interprets B, B interprets A, and there exists this isomorphism, then we can conclude that A is an extension of B. So here we don't require this second isomorphism, so B may not define it. And Ali and I had also proposed one stronger notion, namely solidity, on the level of models. So we say that a theory is solid if and only if for any two extensions of it, if for any two models of it, say M1, Mn2, if M1 interprets M2, M2 interprets again M1, and there exists M1 definable isomorphism from M1 on to this interpreted copy of M1. I put the stars here to indicate that this model may be not exactly equal M1, it may be just isomorphic. So if we have such a situation, then there exists actually a definable isomorphism from M1 to M2. So we have these three notions: tightness, neatness, and solidity. And neatness implies tightness, because if we have neat theory and we add here this isomorphism from B to this interpreted copy of B, then we can conclude that A is an extension of B and B is an extension of A. And solidity implies neatness because if we have some interpretations on the level of theories, then we have these interpretations on the level of models. And if we prove that and if M1 is isomorphic to M2, then they of course have the same theory. And Ali and Ayat proved that the following theories are solid. So Ali and Ayat proved that PA is solid, second order arithmetic is solid, third order arithmetic, ZF, Cayley-Morse theory, and higher order analogs of Cayley-Morse set theory. And Ali and Ayat also proved that solidity is closed under by interpretability. On the other hand, it was shown by many authors that, for example, I sigma n is not even tight. So also it's not solid because solidity implies tightness. And actually any pi n axiomatized fragment of true arithmetic is not tight. Pi 1n comprehension axiom with full induction, actually we can add also some other axioms to it, is also not tight. ZFC minus foundation axiom also is not tight. And ZFC without axiom of power set and Zermelo set theory also are not tight. And in this talk, I'm going to show that for every natural number, there exists a recursively enumerable solid subtheory of PA that contains I sigma n plus exp, but not B sigma n plus 1. Later, I will sketch how we can improve this result to show that there exists such a theory, which additionally does not interpret PA. And later, I will show also that we can improve this one more time to obtain a theory that, in addition, does not prove PA even after adding a true arithmetic sentence to it. So it cannot be the case that we add to this theory, for example, con PA, and we obtain full PA. So in this sense, PA is not in a finite distance. This theory is not in a finite distance from PA. Okay, so let's prove the first theorem. Let's start with some introductory example. So let T be the following theory in the language of Peano arithmetic. This theory say maybe there is exactly one element, and then the inequality symbol behaves like indicated here, or there are at least two elements, and then P holds. And I claim that this theory is solid. So let's prove it. First, observe that if we decide whether there exists exactly one element or there are at least two elements, then we obtain solid theories. So T2 is exactly PA, and T1 is a theory of some one element model. So now, let M1, M2, and M3 be models of T such that in this picture, then I claim that either each of these models satisfies T1 or each of them satisfies T2. And this holds because if M1 is a one-element model, then it cannot interpret PA, so M2 cannot be a model of PA. And if M1 is a model of PA and M2 is a one-element model, then this one-element model cannot interpret, again, PA. So these models need to be need to satisfy the same theory. Okay, but T1 and T2 are solid, so in each case, there exists a definable isomorphism from M1 onto M2. So our theory is solid. And this is actually the general idea. We will find a theory which is an extension of I sigma n plus not B sigma n plus 1, which is solid, and for which these mixed cases, as in this example, are blocked. So there is no possibility to have model of this theory, model of PA, and again, model of this theory with definable isomorphism, and vice versa. Okay, so to find this theory, we will need some reminder. So CT is a theory in the signature that extends the signature of PA by a unary symbol P, and consisting of the following. So PA, axiom stating that the true predicate P contain the arithmetic diagram and commutes with the logical symbol. So that P is So the usual compositional clauses specifying true, and the induction scheme for the full language. And Ali and I had proved that this theory is also solid. Now we can show how we would like to block these cases. So we'll use the following two lemmas. So let M1 and M3 be models of PA, and let M2 be a model of CT. Suppose that M1, M2, and M1 interprets M2, M2 interprets M3. Then there is no M1 definable isomorphism from M1 onto M3. So, and in the opposite direction, there are no mixed cases PA and CT. So the second lemma say that if you have models of PA of CT M1 and M3, and this middle model M2 is a model of PA, then if M1 interprets M2 and M2 interprets M3, then there is no M1 definable isomorphism from M1 to M2. So as I said, there are no mixed cases CT and PA. We'll prove now this first lemma. So assume that we have three models, M1, M2, and M3. M1 and M3 are models of PA, and there exists a definable isomorphism from M1 onto M3. Okay, so let's start exactly as Albert Wieser proved neatness of Peano arithmetic. So first observe that M1 can define injection, can embed itself into some initial segment of M2. It can just use some formula of the form. There exists a, so X, we map X onto Y if and only if there exists a sequence starting with, of the length Y, starting with the element which is 0 in M2, and next elements are obtained by using a successor function in M2. So the point is that M1 can embed itself into some initial segment of M2. And similarly, M2 can embed its arithmetical structure into the initial segment of M3. So composition of these two is also an injection, and it is injection from M1 into initial segment of M3. But M1 knows that M3 is isomorphic to M3, and it satisfies PA. So this injection have to be onto. So all these injections have to be onto. So we have definable isomorphism between arithmetical structure of M1 and M2. But M1 interpret also truth predicate for M2. So, and actually satisfaction predicate. So in this situation, M1 would could define satisfaction predicate for itself, which is contradiction by Tarski's theorem. And this is the end of this proof. So we would like to say that our theories say something like I'm PA or I'm CT. But CT, of course, is not arithmetic theory. We now need to code CT as an arithmetic theory. So we'll need some reminders. So let's start with arithmetized completeness theorem. So we have the following theorem. Let M be a model of PA star, by which I mean some extension of PA, maybe with some extended language, but with full induction. And let tau be some formula. And assume that the set defined the set of sentences defined by tau in M is consistent in M. Then there is a model N such that M interprets N, and for every sentence sigma, if tau holds of sigma in the model M, then N then N satisfies sigma. So N satisfies all the sentences. Next reminder, so let N be a natural number and M be a model of I sigma n plus 1. Let K be a model consisting of the sigma n plus 1 definable elements of M. Then K is sigma n plus 1 elementary in M. K satisfies I sigma n and not B sigma n plus 1. And the standard cut is definable in K by this formula, which which defines the smallest set containing sigma n plus 1 definitions of all elements. And the last reminder, flexible formula. So let T be a theory and gamma a set of formula. A formula kappa is gamma flexible over T if and only if for every formula phi from this set gamma, the theory T plus kappa defines exactly the same set as phi is consistent. And here is the key theorem. Let T be a recursively enumerable theory containing I delta 0 plus x. Then for every natural number greater than 0, there exists a sigma n formula, sigma 1 flexible over T.
Was that sigma 1 or sigma n flexible over T?
Sigma n formula, which is sigma n flexible over T. So this is sigma, yeah, okay. Yeah. Okay, and now we can code CTB as an arithmetic theory. Let's start with fixing some natural number. And in the standard model of CT, we will define a model of I sigma n plus x plus not B sigma n plus 1. And it will be an interpretation H. And we will also define an interpretation in the other direction. So in this model of I sigma n plus x plus not B sigma n plus 1, we will define a model as the standard model of CT. And moreover, these compositions of this interpretations will be parameter-free, indefinably isomorphic to identity interpretations. So it will look like this. We will start in the model, standard model, define some model of I sigma n plus x plus not B sigma n plus 1, and define again some isomorphic copy of the standard model. And all these interpretations and isomorphism will be parameter-free. And it will allow us to build an LPA theory, arithmetic theory, that is bi-interpretable with an extension, some extension actually with CT, but with an extension of CT. We'll just put to our theory enough information about this situation which is in this picture. So let's start with defining H. So let kappa be a sigma 1 formula, sigma 1 flexible over PA plus not con PA. Observe that PA plus not con PA plus kappa defines a set of true sentences is consistent. It is definable in the standard model of CT, and it is consistent because if we take some finite fragment of it, it is just a fragment saying that kappa holds of 7, kappa does not holds of 9, and of course, a set of this form, this finite set is sigma 1 definable. Okay, so now we will construct H. We start in a standard model of CT and construct by this arithmetized completeness theorem a model of the above theory. Then we take a model consisting of the sigma n plus 1 definable elements. And that's all. Oh, we can here note that kappa is a model of I sigma n plus x plus not b sigma n plus 1, as well, what we've seen in the reminder. So now, okay, also note that H is a parameter-free interpretation. Now let's define G. So let delta be the formula defining the standard cut in K. Go further. So since K is sigma n plus 1 elementary substructure of M, and kappa is a sigma 1 formula, then for every natural number, in K, kappa holds of M, if and only if M is a code for a true sentence. So we can define this interpretation in this model K, interpretation of the standard model of truth using delta for domain, unchanged arithmetical operations, and kappa for this truth predicate. Again, this is a parameter-free interpretation. And now isomorphism. So this isomorphism is rather straightforward. We just, if we want to define isomorphism from the standard model into this copy of standard model, we just take some natural number and map it to the x element of K. And this is an isomorphism. In the opposite direction, we have to do a little bit more. So we choose some element of K, find the smallest sigma n plus 1 definition D of X, and this have to be necessarily a natural number. And in the structure, which is defined in this defined copy, in this interpreted copy of a standard model, the structure defined by H is isomorphic to K. So we can find there also an element which is defined by this definition. And we map X to element defined by this definition. Again, both isomorphisms are parameter-free. Okay, so now we can write this theory, which will be bi-interpretable with CT. So we will call this theory T0N. So we put there I sigma n plus x plus not b sigma n plus 1. We put some infinite set of sentences saying that this particular formula which we used in G, this particular formula defines some structure, and we write sentences that this structure satisfies CT. Later, we add axioms saying that if we take this formula, which we used to define isomorphism I, then this formula is an isomorphism from the identity interpretation onto the interpreted G copy of the structure, so to the composition of H and G. So we need to say also that if we use this formula of H in G in the structure defined by G, then we also obtain some structure. And similar, we say that a J is an isomorphism from the structure defined by G. I use these brackets to indicate that this is a structure defined by G into the appropriate copy of it. And that's all. And of course, this is recursively enumerable. We just choose some particular formula to which we use as isomorphisms and interpretations. Okay, now we can prove that this theory is solid, and proof is easy. This theory is just bi-interpretable with some extension of CT. We just put it, maybe I'll go back. We just put it into this theory, information how to build inside a model of CT, information that we can, in this model of CT, build, construct a model, again, of a sigma n, and that we have some particular formula which can use as an isomorphism, and that if we, again, in this copy interpret CT, then this internal copy of CT can define isomorphism by using exactly this formula from its copy. So they are just isomorphic, as they are just bi-interpretable. And solidity is close under bi-interpretability, as I said at the beginning. Okay. So now we will show that mixed cases are also blocked. So we have the following lemmas. So let M1 and M3 be models of PA, and let M2 be a model, this middle one, a model of T0n, and suppose that M1 interprets M2 and M2 interprets M3. Then there is no M1 definable isomorphism from M1 onto M3. And in the opposite direction, if M1 and M3 are models of T0n, and M2 is a model of PA, and M1 interprets M2 and M2 interprets M3, then there is no M1 definable isomorphism from M1 onto M3. Again, we will prove only this first one. So assume that there is this isomorphism. So M1 is a model of PA, M2 is a model of T0n, and M3 is isomorphic copy of M1. So our theory T0n say that it is bi-interpretable with CT. So here we can use interpretation G to build a model of CT, and here we can use an interpretation H to build an isomorphic copy of M2. And because this is an isomorphic copy of M2, we can also find this interpretation of M3 here. So here is some isomorphic copy of M3. And actually, because M2 see isomorphism from itself to this copy of M2, then it can also see that, so define isomorphism from M3 to this copy of M3. So this isomorphism is M2 definable. But if it's M2 definable, then it is also M1 definable. So M1 can define isomorphism from M3 to M3 star. So it can define isomorphism from itself to M3 star. Okay, so we have model of PA, model of CT in the middle, and later again, model of PA and an isomorphism. And this is contradiction by the lemma from the beginning. Okay, so now we can define the solid proper subtheory of PA. So this theory say I sigma n holds and exp, and if b sigma n plus 1 holds, then PA. And if not b sigma n plus 1, then holds T0n. Here we have theorem saying that Tn is a recursively enumerable, which is here. Okay. A solid subtheory of PA that contains.
Piotr, sorry.
Yeah.
So in the middle part, how is this b sigma n plus 1 written? That has to be a single sentence.
Yeah.
So you use finite axiomatizability of what is it? How is it done?
Yeah, that's just the point. You use finite axiomatizability.
Okay.
You branch on whether, you know, the single
Right.
sentence
So this
sigma n plus 1 holds.
Oh, all right. Okay.
Yeah. Yeah. So this b sigma 1 here is a single sentence. Yes. Okay.
And for the
yeah.
and for the negation, so this is the negation of the same sentence, or
Yes.
Yes.
could be just
this
instance.
is a case distinction. Yeah, this is actually a schematically axiomatized theory. If you is it? Yeah, it is. Although you have to check that T0n is schematically axiomatized, but it is in fact. So,
Right.
yeah, it's just a case distinction. You know, either this particular sentence holds, which means that that b sigma n plus 1 holds, and in that case you have all of PA, or b sigma n plus 1 doesn't hold, in which case you're in this very particular kind of sigma n plus 1 pointwise definable model.
Right. And in the second case, you could just have some instance of failure of b sigma n plus 1.
Yes, of course.
Like a simple failure. Okay.
Yeah, but in general, you
specific, right?
You don't quite know what will fail, so yeah, you basically want to just negate the sort of
everything.
Universal formula kind of.
Okay, so this theory is recursively enumerable because T0n is. It contains a sigma n plus x, of course, and does not contain b sigma n plus 1. So we only need to show that this theory is solid. So let M1, M2, and M3 be models of this theory, such that M1 interprets M2, M2 interprets M3, and there exists this isomorphism. Then either each of them satisfies PA, or each of them satisfies T0n, because we showed that mixed cases are blocked. So because both are solid, then in each case, there exists an M1 definable isomorphism from M1 onto M2. Okay, so we have the solid proper subtheory of PA. So we could say, okay, so PA is not minimal, but actually, our biointerpretability, solidity is closed under biointerpretability. And we actually found some theory which is biointerpretable with CT. And actually our theory interprets PA. And this is because T0n interprets PA, and PA, of course, interprets PA. Actually, we can use the same, this is not visible maybe at the moment, but we can use the same formula regardless of n. So we can ask whether there is a such a theory which does not interpret PA. And we answer this question showing that there is such a theory. And we will now sketch the proof. So what is the general idea? The general idea is to modify T0n so that it cannot interpret PA using low complexity formula, where this class of low complexity formula grows larger as n increases. Then we will need to make some another modification to block n m mixed cases for n not equal m. And then we'll write kind of infinite disjunction saying that maybe T0n, maybe T0n plus 1, maybe T0n plus 2. The point is that in which T0n we have interpretation of PA, but the interpretation of the smallest complexity, this complexity is growing. So if we have some interpretation of PA, it can be interpretation of PA only in some initial segment of the sequence. So in some Tn plus k, it is not an interpretation of PA. So it is not an interpretation in the whole theory. Okay, I will now show how to block this low complexity interpretations. So again, we will start in the standard model of CT. But instead of building model of PA and not con PA, and then taking this sigma n plus 1 definable elements, we will build a model of I sigma n plus 1 and not con I sigma n plus 1. And it is enough, because if we take any interpretation, then T0n can embed its cut, some its cut, on its one cut on a cut of the model defined by P. Let's say P is some arithmetical interpretation of an arithmetical theory. So if the formula of P are of small complexity, then this embedding is also defined by a formula of small complexity. So it must be defined on the whole universe of Tn, because Tn have some enough induction to prove it. Okay, so now if P were an interpretation of PA, then T0n would have to prove consistency of I sigma n plus 1, because T0n embed its universe on an initial segment of P, and PA proves the consistency of I sigma n plus 1. So if P is a structure in which PA holds, then on each initial segment of the structure, I sigma n plus 1 is consistent. I sigma n plus 1 is consistent. So if T0n is an initial segment of the structure, then in T0n there must holds con I sigma n plus 1. But we put it to this theory that it's not the case. Okay, so having this and skipping this blocking mixed cases part, we can define we can define solid theory not interpreting PA. So let T0 and tilde be this modified T0n. And now T and tilde is a theory consisting of the following axioms. I sigma n plus x. If B sigma n plus 1, then I sigma n plus 1. Again, here we use the single sentences, finite axiomatizations. So we are on the level of the induction, not on the level of collection, or maybe we are just in PA. And some of the following sets of axioms saying that if I sigma k and not B sigma k plus 1 holds, then holds T0k tilde, so K theory. And we claim that this is a recursively enumerable solid subtheory of PA that contains I sigma n plus x, but not B sigma n plus 1, and does not interpret PA. So it is recursively enumerable, but it is not visible because I skipped the mixed blocking mixed cases part. Of course, it contains a sigma n and not contain b sigma n plus 1. So let's go to the proof. So first, for every n, T0n is solid because of the same reason. T0n is just bi-interpretable still with some extension of CT. These cases are mixed, are blocked. These mixed cases are blocked exactly by the same reason, because T0n is bi-interpretable with some extension of CT. And NM cases are blocked, which we skipped. So this theory is solid. Okay, so now for the not interpreting part. Let P be any interpretation in this theory, and let sigma k be the complexity of the formula of P. Then, for sufficiently large m, greater or equal than n, T0m tilde cannot interpret PA using formula of complexity sigma k. Because we constructed this T0m tilde in such a way. But T0m tilde is an extension of Tn tilde. So if something is an interpretation of PA in Tn tilde, then it is also interpretation in T0m tilde, which is an extension in this theory. So P cannot be an interpretation of PA. Okay, so we proved this theory. But we have one more improvement to do. So let's first observe that if we add to our theory a sentence saying that PA is consistent, then we can prove PA. This is because T0 and tilde proves that not con I sigma n plus 1. So if we add this one sentence, then PA holds. And the motivation for this result is the following theorem by Wilkie. And actually, Ali and I asked this question. So the following theory of Wilkie. So suppose phi is some second order sentence in some special form, and that for all x's, that the sentence for all x's phi of x is categorical for natural numbers, meaning that natural numbers are the only structure satisfying the sentence in the sense of full second order logic. Then there is an arithmetic sentence sigma such that the sentence is true in the standard model. And if we add this sentence to the scheme obtained from this formula, then we obtain full PA. So in a sense, all these schemes of this form are in a finite distance from PA. And we show that with solidity, it's not the case. So we will show that for every natural number, there exists a recursively enumerable solid subtheory of PA that contains a sigma n but not x, and x, but not b sigma n plus 1, does not interpret PA, and does not prove PA even after adding a true arithmetic sentence to it. So I will sketch only the general idea. For this part, does not prove PA even after adding a true arithmetic sentence to it. So we start in a standard model of iterated truth. And actually, this already blocks mixed cases. Then we will modify this this construction of a model of I sigma n plus x plus not b sigma n plus 1 in such a way that the resulting structure will be sigma n elementary and extension of the ground model. And again, we will take an infinite disjunction of the theories obtained. The point is that if we take any true arithmetic sigma k sentence, and then it is true in the standard model of this iterated truth. So if we take n greater than k, then sigma is also true in the model constructed with this h, because it is an sigma n elementary extension of the standard model. But this model H is a model of our theory, and it does not satisfy PA. So for any sentence sigma, which is true in the standard model, we can find model of our theory in which the sentence is true, because this model is elementary, sigma n elementary extension of the standard model, and which does not satisfy PA. And at the end, so in this way, we can obtain this theory, which does not have this Wilkes property, meaning that it is not in the finite distance from the PA. And if you want to obtain theory which does not interpret PA and does not have this Wilkes property, then we just need to make a disjunction from these theories. Okay, and now I have still a few minutes to show some other results on which we are still working, and some questions. So first, we can say that, well, we would like to say that PA is not minimal, because we found a theory which does not interpret PA and is solid. But actually, solidity of this PA strongly relies on solidity of this theory strongly relies on the solidity of PA or stronger theories like CT. So we can ask, is there a solid sequential subtheory of PA that has a model that does not interpret any model of PA? And I don't know answer for this question. Auxiliary, we could ask, and this is a question of Ali and Ayat, is there a solid finitely axiomatizable sequential theory? We can go also in another direction and ask for similar results for Z2. Here we have some partial result, like solid subtheory containing RCA and solid subtheory containing ACA, but we didn't really check whether we can construct such theories on the level of pi11. We can ask also for similar results for ZF. Here also we didn't really check the okay, is that right? Yes, usable here. Okay, and there is also another branch of our research. So I said that there are three notions: tightness, neatness, and solidity. And actually there is the fourth one, called semantic tightness. It is like solidity, but to conclude that there exists an definable isomorphism from M1 to M2, we need bi-interpretability of models. So we can ask what are relations between these notions? Neatness and tightness are syntactical, semantic tightness and solidity are semantical. What can we say about relations? So of course, we know that solidity implies neatness and semantical tightness, and neatness and semantical tightness, each of them implies tightness. So we could ask, for example, whether there is a theory which is tight, but is not neat and is not semantically tight. So it's also not solid. And actually, we answered this question. So we prove that for every natural number, there exists a recursively enumerable, tight but not neat subtheory of PA that contains b sigma n plus x, but not I sigma n. And the proof relies on some properties, use some properties of models of collection, but not induction. But actually, we don't know whether this theory is semantically tight or not. But also, we have a theory that is tight, but not neat, and not semantically tight. And this is a subtheory of PA, and this theory contains PA minus. We actually have an idea how to build a theory on the level of I sigma n, such a theory on the level of I sigma n, but we are still missing some element of the proof. Okay, so we can ask also whether there is a theory which is neat and tight, so satisfies these syntactical notions, and is not solid and is not semantically tight. And we also have such a theory. Well, we have such a theory which is not in the language of arithmetic, and we didn't check properly whether we can code this as an strictly arithmetic theory. So here is this question mark, but it should be that for every n, for every natural number, there exists a recursively enumerable neat, so also tight, but not semantically tight, so also not solid subtheory of PA that contains I sigma n plus x, but not b sigma n plus 1. We could also ask whether there is a theory which is neat and semantically tight, but not solid. We could also ask whether there is a theory which is tight and semantically tight, but it is not solid and not neat. And we really don't know. The problem is with cutting between solidity and semantical tightness. And it looks like we should try to use some other methods than ours here. So we can ask another question: is there a semantically tight but not solid sequential theory? So in total, we have the following questions. Is there a solid sequential subtheory of PA that has a model that does not interpret any model of PA? And this is a really interesting question. Auxiliary, but also independently interesting, is there a solid finitely axiomatizable sequential theory? Questions about similar results in the case of second-order arithmetic and Zermelo-Fraenkel set theory. And question about a theory which is semantically tight, but not solid, and which is sequential. And that's all. Thank you.
Okay, let's thank our speaker. And we'll open it up for questions. So thank you very much, Piotr.
I have a question.
Go ahead, Ken.
Yeah, I mean, it's a historical question as usual. Back in the 20th century, the thing that we knew that sort of connected ZF and piano arithmetic was the fact that neither was finitely axiomatizable and that they were reflexive. They both proved the consistency in pretty strong forms of any finite subtheory. Okay. Now, is that sort of thing a sort of a stepping off point for this very elegant research that you guys are doing today? Or is it subsumed by it? Is it critical to it? I mean, what's the connection, if you would?
Of the connection of reflexivity of this reflexivity to solidity. Yes,
Ah,
that's the
I
question.
guess the question is whether we use reflexivity or so our theory, our basic example of our theory is not reflexive, right? Because for instance, it could if you take say n equals 0, so you're assuming I delta 0 plus x, and you're branching on whether p sigma 1 holds, then that theory won't even prove the consistency of I sigma of I delta 0 plus x. I don't remember exactly the exact technical details of what Piotr described, but in general, it doesn't have to be reflexive. On the other hand, all the models of our theories, the ones that got described, have the smallest cut, smallest definable cut, which is always a model of PA. So they do at least define, they do at least prove the consistency of their finite fragments on a specific cut.
But the results also extend to ZF, right? I mean, a family of these results.
I would expect they eventually extend in some form, but we have not done an in-depth study of this.
Ah,
And
okay.
I expect you need to have some sort of V equals something axiom to get a full analog, right? Piotr, am I right that you should expect this? I mean,
Yeah. Well,
you
I
probably
mean,
do want to
especially
be working with a definable well-ordering of the universe, at least in some of the cases that we're considering.
yeah. Actually, I have some idea with V equal L. The problem is okay. If we don't demand on the power set axiom, then probably we can try to say something like Z2, so second order arithmetic, or ZF. But probably we could try to use V equal L. Yeah.
Thank you.
Other questions? This is not so much a question as I just want to see the definition of the T ends, the T0 ends again.
T0n, yeah?
Yeah.
In this basic form. T0. Okay, here it is.
This is T. Okay.
That's
Oh,
Tn already,
T0,
right?
This is Tn. This is Tn.
Tn.
Okay.
Yeah.
Okay, and T0n.
Okay. So
This is T01.
P sigma. Okay. And then, okay.
Yeah. So you're in a very specific pointwise definable model of I sigma n, which happens to be bi-interpretable with a model of TA plus truth, plus full induction for truth.
Interesting. All right. Thank you. Other questions? Okay. Let's thank our speaker. Thank you, Piotr. Next week, I think we have Albert. Is that right?
We have Albert.
We have Albert
Yes,
Visser.
we have Albert Visser about his work with Ali again, and this is about those sequential theories that have axiomatizations of finite quantifier complexity.
Okay. All right. So please come back for that. And thank you all for joining.